Um, I'll try. In fact, I was told that organizer is not supposed to talk. So I took out my name out of the list of speakers a couple of months ago. And then uncertainty kind of helped me. The program had to be shifted back and forth so many times that without a joker, just putting myself where I could to fill the gap, I couldn't find it out. Now probably I will have to cut it significantly, but there is more uncertainty. I'm very pleased that I found some time, because I'm very pleased to talk about paradoxes connected to Aharonov-Bohm and Aharonov-Casher effect. So I will not waste more time of general issues. And I want to present these paradoxes in a simplest example I know. In a simplest quantum experiment is a Mach Zehnder interferometer. It is quantum if we use one particle. We can tune it in such a way that every time we send it from one side, it goes to one particular port. And if we tune it this way, then if we send it from another side, it will go to another particular port. Now, so we can look on this situation. We send one from other side, another from another side. We started differently. We end up differently. In between, things seems very similar. So when we start, here in between, there is a 50% chance to find it in one place and 50% chance to find it in another place. So what is the difference? There have to be difference between these two cases, because we started with different quantum states. These states should be different. And the difference is a relative phase. Here we have a 0. We can make it 0 phase, define it. 0 phase, if here it's 0, if here it's plus, here it should be minus. Now, this plus will remain all over in the first experiment. And this plus will tell us where to go at the end. It should go this way. And in this experiment, it's just here, so it's minus. So it will go the other way. So what's going inside Mach Zehnder interferometer? We have a relative phase between two wave packets of a quantum particle. Now, what's in this language Aharonov-Bohm effect? We have the same Mach Zehnder interferometer with charged particle, and we tune it in such a way that it go one way. Then we introduce a solenoid inside. Now, this solenoid doesn't have any field outside, but when we send a particle, if we tune correctly, then it will go the other way. So this is a change. Two identical Mach Zehnder interferometers, and we send from both of them, we start from the same side. So we expect them to go to up, but this solenoid will do something. It will go down. How we can understand it? In this first interferometer, we know the entering phase was plus. The ending phase was plus, because in this way, this explains why you go here. But here, we started with plus, and the end, we go this way. So we know we ended with minus. So this solenoid somehow changed the phase from 0 to pi. Now, it's not clear, at least the standard theory as we had, it was beautifully explained by David Gross. We have a gauge symmetry here, and so we cannot really say where it's happened. The solenoid caused the relative phase. Clear, without solenoid we didn't have it. But the time when the phase is gained depends on the choice of gauge, and therefore it is unobservable. We started with plus, we ended with minus. We know because we have this outcome, but we don't know where. We can use one gauge, continuous gauge, and then it depends on this angle between how we look from here to the particle. And if it's I theta over 2, in the end it will be just pi. We'll get this minus sign. Or we can have a singular gauge. Then nothing happened here. There is no vector potential here, so nothing here. It remained plus until we come to this place where it flips from plus to minus. But the singular gauge, maybe in another, we can fix it other way. So minus will start from here. It was plus only up to this state. So the solenoid goes a relative phase, but the time when the phase is gained depends on the choice of a cage, and therefore it is unobservable. So I will say, I call it paradox. I think in the classical language it's really paradoxical. At every place on the path of the wave packet of the electron, there is no observable action, but nevertheless the relative phase is obtained. Because we can choose a gauge and show that there is nothing happened in every place we want to consider. And this paradox, I believe, will stay, and this is what makes Aharonov-Bohm effect interesting. But still, I want to talk about some other paradoxes. So the next paradox was kind of trying to say that the first paradox may be incorrect. The relative phase is observable locally. Therefore, the time of change of the relative phase can be observed, in contradiction with the fact that it is a gauge-dependent property. Of course, this became a paradox if this sentence is correct, that the relative phase is observable locally. It's not common knowledge, not obvious, so what will follow, I will discuss this. But given, if we can go and locally make a measurement and define what is the phase, we can find where it switched from plus to minus. And in contradiction to the fact that I said that it's not physical, it depends on this property, it's just gauge property, therefore it's not observable. So why I believe that the relative phase is measurable, and let's talk how we... First, when we write it in this way, we have probability half find it here, probability find it here, so it looks like local measurement don't give us anything. But just, we can rewrite this, okay, this just showing that A is in one location, B is in another location, and this is a state, and we can rewrite this state in the following way. Just define one particle in A as A, and zero particle in A, it's a different state. So we can rewrite this state in this form. We have place A and B, and this quantum and the quantum state of place A is that there is a one particle there, and or zero particles there, and then we have this kind of state. This looks like EPR state, and we all know that the EPR state, when we have two spin half particles, EPR-Bohm state, we can find the phase because there are correlation. EPR states are all anti-correlated. Change the phase, they are not correlated. Looking on local correlation, EPR correlation observable locally, and therefore we can find the phase. Again, we cannot find it on one particle, but this is not important. All this experiment can be done on ensemble. We have many equally prepared Mach-Zehnder interferometer with a solenoid or without solenoid, and with the solenoid we test in different places where the phase changed. So this is just kind of a hint. But this is more than a hint. In fact, Hardy proposed to measure a relative phase of, for the photon. And the experiment is following. We have this photon separated in two wave packets, A and B, and then we bring coherent state locally. One coherent state here with coherent state alpha, and another alpha coherent state in another place. And now we make this experiment and we put a beam splitter and we look on correlations. Now playing with alpha, in the end we will find the phase. And the explanation really is that when we have a product of coherent states, here and here, somehow the formula disappeared, but probably you all know that if we look on this coherent state times this coherent state, we can represent it as another coherent state of a superposition of A tag plus B tag. And if we have a relative phase, this phase will be on every particle. Okay. Oh. Okay. So the first experiment for photons, but this is not very interesting. We're talking about Aharonov-Bohm effect, and the standard Aharonov-Bohm effect is for charged particle. If we use pions, that conceptually it's also Aharonov-Bohm effect. So let's use pions. Relative phase of a charged pion is observable locally. Some people kind of say it's problematic. There are all kind of super selection rules which says that we cannot have a coherent state with different charge. But Yakir will help us here too. He wrote a paper with Larry Susskind that no problem. We can find a relative phase between different charge states. So in principle, we can have a coherent state of pions, and the superselection rule, it's really an illusion. If you talk really about proper relative state properties, no problem. Not really no problem, because it's really only a Gedanken experiment. This coherent state, although we can create it, it's very unstable because of strong interaction, strong electromagnetic interaction. But conceptually, it is measurable. Now, if I want to discuss the standard Aharonov-Bohm experiment, so we have electrons. With electrons, there is a difficulty. No way to find a relative phase of an electron locally. There is no possibility to do something here and locally something here and to find what is the relative phase, even if we have an ensemble. However, given another particle, another fermion, the problem with electrons is fermion. Given another, let's take positron, and we know the state of the positron, then no problem. We can find the phase. One way to annihilate, and then we have two photons, one photon in superposition with the same phase, and we can find it. So all this tells us that we can measure relative phase. But if we can measure a relative phase, then we have this contradiction. If we can measure a relative phase, then we can find where exactly the phase flipped from plus to minus. And this was supposed to be unphysical property. Now, the last slide about measuring with electron really tells us the hint of what's going on here. If the measuring device requires this positron, a charged particle, if it's charged particles, it also fills the Aharonov-Bohm phase. So what will happen? Let's say we have particular gauge and we get phase phi. But the positron will get phase minus phi. When we make annihilation, everything is cancelled. No effect. Now, with coherent state, maybe it's a little more complicated, but the same idea. What's coherent state? Here, this formula which I was looking for, it's still here. This it's just the coherent state, local, even it's local here and local here, can be presented as coherent non-local state with this phase. And every particle in this superposition, since it's both here and here, will get the same Aharonov-Bohm phase. So after we make this measurement with this coherent state, they have relative phase, and all effects will cancel. The same effect on electron, the same effect on the coherent state. This was really with pions. On pion, one pion and pion of a coherent state. So the paradox 2 is resolved. The relative phase of the measuring device, which measures the relative phase of the particle, also depends on the chosen gauge. In fact, local outcomes are not influenced by the solenoid, only the interpretation. And even the interpretation is gauge dependent. Because we can have this phase, this gauge, then nothing happened until here. No vector potential, so our measuring device don't change phase, our particle don't change phase. Now what's happening here? Since the measuring device changed its relative phase between the parts, then the same correlation here will tell us, the phase now is minus because the measuring device changed. And this will be correct because this gauge will also change the phase of a particle. So everything fits correctly, no problem. Again, it will be here, everybody will agree. So paradox 1 remains intact. In every place of the parts of the wave packet of the electron, there is no observable action, but nevertheless the relative phase is obtained. I say I still can continue to other paradoxes. Other paradoxes involve duality between Aharonov-Bohm and Aharonov-Casher effect. We have a symmetry of interaction between neutron with pointed in a z direction and electron. And therefore, if we will consider Aharonov-Bohm as the same Mach-Zehnder, and the solenoid is many, many neutrons pointed up to another, which makes solenoid. And now we change neutron to electron, electron to neutron. We'll get this configuration. And the symmetry of interaction should tell us that the motion of an electron here should be the same as the motion of a neutron here. The motion should be identical. Now, the problem is that Aharonov-Bohm effect clearly is topological because there is no force here, there is no field here, nothing is here. However, in Aharonov-Casher effect, things are not so simple. There is a field here, there is an electric field here. This is a neutral particle, so maybe on the first side, no force. But this is really not true. This neutron in Aharonov-Casher effect does feel force. So we have the following paradox. We have we have electron with solenoid, electron without a solenoid. The behavior of a particle should be the same, because really, as we saw, it doesn't change anything, only something later. Now, clearly, if we have a Mach Zehnder with electron, a Mach Zehnder with neutron, the motion of a particle should be the same Mach Zehnder interferometer. Now, because of duality, if we have this Aharonov-Casher effect, we have a neutron and a line of charge inside. This should be identical to this case because of duality between AB and AC effect. But if we have this dual to this, all equivalent, this should be equivalent to this one. But here there is a difference. On neutrons there is a force. And clearly there is no force here, there is nothing here. And there is no force here. So, this is a paradox. It cannot be that we have four things, A identical to B, identical to C, identical to D, but A is not identical to D. So, it's all because there is a force. Let's talk about this force. I just said that there is a force. I said that there is a force. Let's consider a somewhat similar configuration. Maybe it's easier to see how the force arises. The same story. This is a line of charge, and this is how a particle goes in different times. And the claim is that here we will have force in this direction, and here we'll have force in another direction. If we'll have the same, on both sides the same, this will not change much. Again, there will be no identity. But what really happened, even that we have force here this way, and here we have force in this way. How comes? So here the Newton slow down, here they accelerate, and why? In fact, Boyer was first to mention this, and he correctly said that the neutron is not a two monopoles. Neutron is a current loop. The correct model for a neutron is a current loop. Now, if I have a current loop moving, you all know that it has an electric dipole moment. Now, this electric dipole moment entering fields, so the electric field changing. Of course, there is a force on this dipole. Very simple. This explains why these forces. And then Yakir had this work of Boyer and said, no way, cannot work. And he presented one more paradox. I'll call it Yakir's paradox. And he says that if Boyer is correct, then we can get energy for nothing. And how we do this? We just introduce two mirrors here and let a neutron go back and forth and using this force. The point is that when neutron goes this way, so we go back and forth. When the force goes to the right, the force is to the right. When it goes to the left, the force is to the right, to the left. And no source of energy here. Why it is, again, because the electric dipole moment depends on velocity. If we switch velocity, it will be different sign. So both velocity switched and the dipole moment switched. So we have all the time force in the same direction. Of course, if we put it in another place, we will lose energy, but we'll put it in the right place. So we'll have something, it starts slow, and then it will be faster and faster and faster, and let's go faster. Okay. One more paradox, very quick. It's a related one. A cannon with no recall, old paradox. If we have this current loop, which I was talking about, let's say made of two disks, two charged disks rotating in different places, and then later we put some friction between them so they stop. When they stop, electromotive force, and we will have electric field outside, which will kick this particle out. But this current, this time, doesn't move. So there is no force on this current. So the current, the disk will stay in the same place, but this will move. And this is really kind of sound paradoxical. We have something, we have a cannon without recoil. Sounds impossible. So the resolution to all this paradox is really what's called hidden momentum. I called it rediscovery because we didn't know about it, and to answer the Boyer, we rediscovered it. And what it tells us that if we have a current loop in an electric field, it will have a linear momentum. Nothing really is moving here, but there is the total mechanical momentum in this current is not zero. It will be to the left. Altogether, there is also pointing vector momentum of electromagnetic field. Altogether, it's zero. And this really tells us why it should be there. There is a hidden momentum inside the loop here. So what happened when we stop it? This hidden momentum, which was able to stay here without doing anything, will be transferred to the tube, and this will go there. So there is no really a cannon without recoil. And the same will answer other paradoxes. Resolution of energy paradox. Unfortunately, we don't have a source of energy for free. It is true that the force is not zero, but the acceleration is zero. How it comes? Because the force is dp dt, and the momentum is really, we have two parts, this kinetic part and this hidden momentum. Now, when we're in different places here, different strengths of field here, different hidden momentum. And all this force is responsible for the change of this hidden momentum. It exactly equals to the change of hidden momentum. So what's remained, that the acceleration is zero. So it moves without acceleration. And of course, it answers our basic paradox that here we have all these were equivalent, and these were not equivalent, because here the force is not zero, and here it's force zero. But what was important is the motion of a particle, not about forces. And even the force here is not zero, the acceleration here is zero. Of course, acceleration zero here too. So the particle, both here and here, moves exactly in the same way. The motion of a neutron inside the interferometer is the same, with or without the line of charge. No paradox. Okay. We remain with paradox 1. At every place on the path of the wave packet of the particle, there is no observable action. But nevertheless, the relative phase is obtained. And my conclusion is that paradox 1 is unavoidable property of both Aharonov-Bohm and Aharonov-Casher effects, which makes them non-local, topological, and very interesting effects. There is one thing missing in my talk, and I think since we have 2 hours for lunch, the resolution of all these other paradoxes was this hidden momentum. I didn't tell how this hidden momentum happened. I'm not. My idea now maybe not to tell you how it happened, but to give you one more paradox, a simple paradox without solution, which will give you a hint to think where the hidden momentum arises. Let's try. How comes hidden momentum? I never said so. So if you really want to answer, there are all kinds of models. It depends, and you can look in this paper. But you can start with this paradox, and probably you will find out for all models how it goes on. The paradox of 2 Lorenz observers. We have charged particle, charged plate, and 2 Lorenz observers. We have Alice sitting on an infinite charge plate and throwing a charged particle. And we have Bob moving with constant velocity. This constant velocity is equal to the horizontal component of the velocity of this particle. So this is Alice's view. Now let's try briefly to consider. No, this is Bob's view. What Bob's view sees that the particle is thrown vertically, and we have this infinite charge plate moving. And what I will do now, I just consider the motion of this particle both by Alice and by Bob. Alice's view. We have this infinite plate, we have field up, this is field. Let's take in this plane, she throws a particle, and it probably will be a parabola, but it's easier to see maybe from the side. Not three-dimensional view, it's nice, but maybe it's easier to see it this way. This is infinite plate. We have a field goes up. We have a force, electric force up, and we have a parabola, and we can write equation, constant velocity in x direction. We have equal acceleration in y direction. We have a parabola, and all is fine. But I want a little more computation. I want that Alice will calculate what Bob will see. So there is Bob, and he moves with this velocity. So this is what Alice thinks happened to Bob. Since Bob moves with this velocity, horizontal velocity equal to the initial velocity of a particle, so all what's happening, just this should be cancelled. So she says that what Bob will see, x naught equal x0, constant. It means the particle will go in straight line with this acceleration. So this is the motion of a particle as Alice calculates for Bob. Think correct. So trajectory is a straight line. Alice says to Bob, you will see a straight line. But Bob likes to calculate himself. So this is Bob's view. This is what happens to him. He throws it up, and there is this charged plate moving, and this charged particle moving with Alice. So he understands that because his velocity is equal horizontal part to this one, so it's really vertical. The particle thrown up vertically. Now, since this infinite charge plate moving, we have a magnetic field. This is in red. If current is like this, so here we'll have magnetic field. This is a magnetic field. Now, we have a particle moving up, and we have magnetic field this way. So, in addition to electric field, electric force, electrostatic from electric field force up, we have a magnetic force there. So, although we start vertically, he will say, no, it will not continue to be vertical. We start like this, but there is a magnetic field inside. So, it should go on a curved line. So he says trajectory is a curved line. She says trajectory is a straight line. Again, it's not that she says that she sees it. Maybe different observers see different things. No problem. She sees that Bob sees a straight line. And Bob says, no, I should see a curved line. So this is paradox number 6, and here I will stop.
Question, I think. On your trying to measure phase within the interferometer locally, what does the apparatus look like to measure phase of the waves that are neutron waves locally inside the interferometer? What would the apparatus look like?
Okay. Since what's important for me is the conceptual thing, maybe the simplest way is not one which I presented because it was nicer. This coherent state, coherent light, and whatever. But the simplest way to explain it is the following. Let's say I have a photon here and here. I have a 2 spin-half particle in magnetic field here and here, both down. Now I arrange it such that they can absorb a photon and flip. So when I have this interaction starting with A plus e to the I phi b, after the interaction I will have up plus e to the I phi down, up down plus up down plus e to the phi down up. So now I have an EPR state. And then I bring Stern-Gerlach and we'll start measuring correlation of spin of this spin half particle. So conceptually, no problem. If we have a photon in A plus e to the IB phi, it's the same non-locality as an EPR type non-locality.
Stern-Gerlach is then you have an internal interferometer. So in order to measure phase inside of the interferometer, to answer to my question, relative phase inside locally, you have to have another interferometer. Stern-Gerlach is a type of interferometer.
Okay, if I have my interferometer, I will come here to this particle, will put some device, destroy the particle.
Yeah.
And another one here. I don't care because I have many of them. It's not that it's not a non-demolition measurement; it's a demolition measurement. I have a large ensemble of all this particle, and every time I decide to test if it's happened here or it's happened here, I can bring my Stern-Gerlach device here, or I can bring a device here to see when the correlation will change. The result will be they will never change. The correlation will remain the same all the way.